Welcome to this primer on functions. In this lecture, we'll learn the notion of composition of two functions. And let us recall what we need. In fact, we don't need anything. We just need to know the definitions, meaning what is a function, what is image, pre-image, injection, surjection, those things. And the notion of bijection. So a bijection is nothing but a function which is both injective and surjective. That's all. Here is one problem for practice. So in the last lecture, we saw this object. And in this lecture, we will see that this is actually just the Cartesian product of this two-element set n times with itself. Okay, so do this. And now let us continue. All right, so now what we are given is two functions, f and g, with the special situation that the target of f is same as the domain of g. So in such a situation, what one can do is create the composite of g and f. And how does one do it? One just superimposes the two pictures. Since the target of f is same as the domain of g, one can indeed superimpose. Okay, so this now gives us the composite of f and g, and it is supposed to be a function from x to z. So what happens in the middle does not matter anymore. And what happens through it is what is important. So all we are interested in, if we start our journey at a point in x, we follow the arrow, we reach to some point. That is the image of this point under the composite of g and f. So here I have another picture which does precisely that. So suppose we start at this point, we follow the arrow, we reach here, and here indeed we reach there. We start at this point, we follow the arrow, we reach here, and here I've drawn the same thing. And similarly, you can see for every point. So the notion of composition is a very natural notion, which I have explained via a diagram, but we of course need to discuss the formal definition. So formal definition is very simple. Let f and g be functions. So here already y and y, so the target of f is the domain of g. Then the composite, maybe it's a good idea to expand this, but I don't have enough space. Anyway, forget it. So the composite of f and g is defined as the map, which we notate as g, then we make a circle, and then f, so perhaps use a different color. G, circle, a small circle, and f, and the domain is the domain of f. The target is target of g, as little x goes to g of f of x. Okay, maybe I'll write that again. Little x goes to g of f of x. Exactly what we were doing here. So if this is little x, you apply f and then you apply g. You have little x, you apply f, and then to the result you apply g. So in this picture, if this is little x, this is fx, and this is g of f of x. Okay? So I hope this is clear. That's the definition of the composite. And we also saw the notation for the composite. This is the notation. But I also want to discuss the commutative diagram for it. So usually all this can be depicted very neatly using a simple diagram. So we have f, this is y, then we have g, this is z, and this arrow is the composite. All right. So you pick a point, you apply f, then you apply g, or you take this route. It's the same thing. So this diagram is a defining diagram for the composite. It's the same thing as this, but it's just the bare bones version of this picture, and much more useful, because when you have infinite sets, you cannot make these dot diagrams. But this, of course, is still meaningful and also very useful. Okay. So this is composite of two functions. And before we continue, let me discuss one property. So here is one property. Lemma. So let f x to y, g y to z, and h z to, wow, I'm out of symbols, so I'll just say omega be functions. So these be given. So then what one can do is first take the composite of these two things. One will get a function from x to z, and then compose it with h, because the target here is z and the domain here is z. Or one can first compose these two things and then compose with it. So what we are saying is that f composed with g composed with h is same as f composed with g, and then you compose it with h. It's a very straightforward lemma, but still I wanted to do it. So proof is very simple. Actually I've written something nonsensical. So what I wanted to write was h composed with g composed with f is same as h composed with g and that thing composed with f. Okay? So I hope you see that this is trying to say something. This is not a trivial statement. Although by the virtue of this lemma, we may drop these brackets because it doesn't matter how you put the brackets, it's the same thing. So one may drop these brackets. All right, so let's prove it quickly. So let x in x be arbitrary. We want to show that if you apply x to the left side or you apply x to the right side, it's the same thing. Okay? So now, what is the left side? The left side is, by definition, this is equal to what? This is equal to h of g of f of, or g composed with f of x. That's by definition, which is equal to h of g of f of x, which is also by definition. And similarly for this, if you just parse this, you will get the same expression. And therefore, these two things are equal. So it's a trivial thing, but still. And in terms of diagrams, it's perhaps more illuminating. You have this function, then you have this function, and then you have h. So what we are saying is either you take this route, so this would then be h composed g composed f, or what you can do is make this highway. So this would now be seen as f composed with h composed with g. And obviously those two things are the same things. So in the first picture, you were first directly going to z and coming here. In the second picture, you were coming there and then directly going to omega. Okay, so it's a simple lemma. Now let us continue. The inclusion map. This has nothing to do with the composite. It's a very simple, straightforward definition. So suppose A is a set and X is a set, where A is contained in X, and everything is non-empty. I am not writing that. So one can define what is called the inclusion map corresponding to A. And it is just a map whose notation is I, and then we make a subscript A. The domain is A, the target is X. What does it do? It takes a little a in A to A. So it just takes a symbol and doesn't do any processing, just returns what it eats. Okay? This is called the inclusion map, and the name is self-explanatory. Okay? Fine. This is just some definition. And here we have sort of a cousin of it, the restriction map. So suppose we have been given a function from a set x to a set y, and we are also given a subset of the set x. Then what we can do, we define the restriction of f to A as the map. By notation, it is this. So we write f, we make a vertical bar, and then subscript it with capital A, whose domain is A, and target is as the target of f. What does it do? It takes something in A and spits out f of A. So again, it is not doing anything very fantastical. It is just whatever f was, its domain was bigger. Now the domain is smaller. All right. And if you want to think of it as a composite, what you can do is you have x, you have the function f, you have this inclusion map. This composition, which deserves a different color, is just the restriction of f to a. So just realize this, nothing. This is the only reason why I discussed these two concepts. These two are frequently appearing concepts, inclusion map and restriction map, everywhere in mathematics. But they are so simple that they could have been done at any time. Anyway. And finally, composition of two bijections. So suppose f is a bijection and g is a bijection. Then we want to show that the composite, which is of course a map from x to z, is also a bijection. Okay. So first, what should I do is really, instead of bijections, let us just show injections. So composition of two injections is an injection is what we are going to do. Okay, so let g composed with x, g composed with f of x is equal to g composed with f of x prime. All right, and what we want to do is want to show that x equals x prime, right? We want to show that this is an injection, meaning it is an injective function. So what we need to do is, whenever you feed it two inputs, x and x prime, and find that they give the same output, you need to show that actually the inputs are also the same. So what this implies is g of f of x equals g of f of x, which implies, since g is injective, this implies f of x equals, sorry, what have I written? This is x prime, equals f of x prime, which implies, since f is injective, that x equals x prime. And that's it. That shows that the composite is injective. And diagrammatically, injective functions are denoted like this. So we make a little hook. This is x, this is f, this is y. It's not necessary that we do it, but we may just make a hook, and that denotes injectivity. So if you see two consecutive hooks in a diagram, when you see, a hook followed by a hook, you can again put a hook here. That's all that this lemma is saying. Okay, and similarly for surjective functions. So we proved it for injective functions. This is also true for surjective functions. So here, instead of injections, write surjections. Okay, and I leave the proof to you, but diagrammatically, this surjectivity is written or denoted by a double arrow. Here we make a double arrow, and this just means that this map is surjective. So this is f. This means that g is surjective. And what the lemma says is, when you see double arrow consecutively, what you can do is, in this composite arrow, you can make a double arrow in the, you can also make the double arrow. So in the injectivity thing, you see the thing happening in the tail, and in the surjectivity thing, you see thing happening at the head. Okay. And yeah, that's it. That covers our lecture on compositions. And I'll see you next time.